Hi, welcome to Office Hours, virtual office hours that is. This week the problems have been selected to help you with your upcoming exam, so I hope you'll give them your full attention. First problem concerns kinematics. Not exactly the worst possible case, but pretty close. Find the velocity and acceleration of a point moving along a curved path relative to a rigid body, which is itself moving with respect to the ground. Watch this. In this next problem, a hamster at point B is running on a circular track. The track has an angular velocity of omega and an angular acceleration of alpha. The hamster is moving with a velocity v measured relative to the track, and this v is increasing at a rate v dot. What you're to do is to find the velocity of the hamster with respect to the ground expressed in terms of the body coordinate system's unit vectors I hat and j hat. Similarly, find the hamster's acceleration with respect to the ground expressed in those same unit vectors. The first step in solving this problem is expressing all the known quantities in vector terms. The angular velocity omega is equal to omega times k hat. The angular acceleration is alpha times k hat. The position is simply r times j hat. And the first of the subtleties is recognizing that vrel, the velocity of the point with respect to the body coordinate system, is simply v times I hat. Now the next one is even a little trickier, and that is the acceleration of the point relative to the body coordinate system. That is to say, AREL, in this case, has two components. It has a tangential component and a normal component. Tangential in the direction of the track's rotation, and the normal toward the center. The first of those, the tangential component, is simply what you were given, v dot times I hat, whereas the component toward the center of the circle is minus v squared over r times j hat. All right, solving for the velocity of B is omega cross r plus vrel. We simply substitute in our known values, and you quickly come to the result shown here in the box. The velocity of the point with respect to the ground is v minus omega r, all scalars, v minus omega r times I hat. To find the accelerations, we use the familiar acceleration formula, substitute in the vector quantities that we derived just a moment ago, and carry out the vector operations, and you get this result. The acceleration of point B with respect to the ground, expressed in terms of the unit vectors I hat and j hat, are the quantity v dot minus alpha r times I hat plus the quantity 2 omega v minus omega squared r minus v squared over r times j hat. And there you have it. All right, the next problem involves finding the equation of motion for a system. You're going to have to identify the number of degrees of freedom, identify kinematic constraints, draw free body diagrams, apply Newton's laws, and put them all together to find the equation of motion. Watch this. So here's the problem. A mass is connected to the ground by a damper with damping coefficient C. A massless pulley is connected to the ground through a spring with constant K. The mass is connected by an inextensible cable to the ground. The cable wraps around the pulley and is in a non-slip relationship with the pulley. Gravity acts. So the question is, How many degrees of freedom does this system have? How is Y1 related to Y2? And finally, what is the equation of motion for this system? So, first question, how many degrees of freedom? There's two rigid bodies in planar motion. So, in the unconstrained condition, there are 6 degrees of freedom total. X1, Y1, theta 1, X2, Y2, theta 2. The walls constrain the pulley, removing a horizontal motion and 1 degree of freedom. The walls constraining the mass prevent horizontal motion and rotation, eliminating 2. So you got 3 possible degrees of freedom, Y1, Y2, and theta. The non-slip condition between the inextensible cable and the pulley eliminate another, leaving you with 2. So Y1 and Y2 are possible degrees of freedom, and the fact that the cable is inextensible, we can see that there's got to be a kinematic constraint between Y1 and Y2. That eliminates yet another, leaving us with only 1 degree of freedom, Y1. So, number of degrees of freedom are exactly 1. The next task is find out what this relationship is. So, the second part of the problem, to identify how Y1 and Y2 are related, consider this diagram. In blue, I have simply replicated the original diagram, and in red, illustrated a hypothetical motion of the pulley and the mass. And here we do a little math. You can see before the motion, in blue, the length of the cable is L1 from here to here, plus pi r, half the circumference of the pulley, plus L2. So that's the length of the inextensible cable. After the motion, shown in red, where you see this motion Y2, notice it appears on both sides, Y1 on this side only, L1 plus Y2 minus Y1, and then we add the half the circumference of the pulley, and then L2 plus Y2 on the other side. When you subtract these two, you are left with the kinematic constraint we seek, which is that the displacement of mass Y1 is twice the displacement of the pulley Y2. So, first step, free body diagrams for the mass and the pulley. For the mass, there's an upward tension, T, and a downward weight, mg, and a downward force from the damper, C, Y1 dot. For the pulley, there's a downward force from the spring, K times Y2, and a downward force of 2 times the tension, because the cable on each side, both sides of the pulley are pulling downward. So here we sum forces in the Y1 direction. We get the T minus C Y1 dot minus mg equals MA, M times Y1 double dot. Rearranging that, we get this, My1 double dot plus Cy1 dot minus T equals minus mg. From the pulley, summing the forces in the Y2 direction, minus Ky2 minus 2T equals 0 because the pulley is massless. Using this expression to solve for the tension's equal to 1/2 Ky2. We substitute this back up into here. We get this expression, My1 double dot plus Cy1 dot plus 1/2 Ky2, that's the tension, and on the other side is equal minus G. In the next line, we substitute for Y2 its kinematic constraint, expressing it in terms of Y1, and we are left with the final differential equation, the equation of motion, the single equation of motion for the mass pulley system. All right, so that's it. Good luck with your exam. We'll see you next time.